Good afternoon. I just want to talk to you a little bit about the kinetic molecular theory and gas laws. We're going to start with pressure, temperature, and the kinetic molecular theory beginnings, just to try to get our feet wet and make sure that we understand what's going on here. So, having said that, let's go forward. Random thoughts. We lived immersed in a gaseous solution. We're surrounded by basically an ocean of air. We live at the bottom of the ocean of air. And we have to think about it like that. It's a fluid that surrounds us all the time, and we're always in it. And we don't even really think about the fact that we're in it because we don't feel like we feel it. We also know that pressure goes from high to low. If you think about weather systems, high pressures are always pushing out low pressures. It's never low pressures pushing out high pressures. It's always high pressures pushing out low pressures. So we need to make sure that we understand that as well. So just some random thoughts that we need to make sure that we keep in the back of our minds, that we deal with and live with, and we've known for a long, long time. We just don't really think about it because it's always there. So what are some properties of gases? Well, there are only really 4 quantities that we need to be worried about when we define gases. We want to know the quantity of the gas. That means the number of moles. We want to know how much gas is there. We wanted to know the temperature of the gas, but we have to be really careful because in this particular case, we need to make sure that the temperature is in Kelvin, because if it's not in Kelvin, then we have a chance of having negative values in places that we cannot have negative values in. This is one of them, the volume in liters. Volume can't be negative. If I have matter, it cannot have a negative volume. So we cannot have negative temperatures. And unfortunately, the Celsius scale does have negative temperatures. So all of the units of temperature that we use here are going to have to be put into Kelvin. Just get into the habit of it. If you get into the habit of it, it always happens the moment you see gas laws. Pressure. This is another thing that we need to know. So these are the 4 properties of gases that we're always constantly looking at when we're talking about gases. These are the 4 main things that when we talk about states of gases and what gases are doing, these are the 4 things that we need to know the most about. So we also know that gas uniformly fills the container that it's in. So if you have a container of gas, like a balloon, it will fill the container completely up. It will actually expand an expandable container. But if it's not expandable, it will fill the container up until it cannot fill it up anymore. So that means gases are easily compressed. So if you have a non-expandable container, you can put gas in that container until you can't put any more. It's compressible. They mix completely with any other gases. So when we think about the ocean of air that we live in, there are a complete mixture of gases. And depending on where we go, there will be different gases depending on what's going on. You know, in different parts of the city, you might have different smells because there are different activities going on at different times. And a vapor is a substance that's usually a liquid at room temperature. So for example, gasoline is called a vapor because it's not a gas at room temperature. At room temperature, gasoline is definitely a liquid, but because it's very volatile and it forms a vapor very easily, in other words, it evaporates very easily, it can also be a gas. And so we call that thing a vapor. So there's a difference between a gas and a vapor. A vapor is a thing that is normally considered a liquid at room temperature, but because of its volatility, its ability to evaporate easily due to the temperatures, it can become gaseous at that point. So those are vapors, just to make sure that we have an idea. So gasoline is considered a vapor. So what is pressure? So we kind of understand temperature, we kind of understand volume, but we need to understand what pressure is. So pressure is basically the force that a gas exerts on its container. So we're always thinking about the force being exerted. So this goes back to that idea of physics that we've had, that there's always a force in action. And so we're going to measure pressure in that way. So force is the physical quantity that interferes with inertia. That means things in motion can stay in motion, or things at rest can stay at rest. So if there's a force acting upon those things, it changes that inertial balance that might be there. So gravity is the force responsible for weight. We know that because of the physics that we've had before. So force responsible for weight, that's gravity. Okay? So pressure is defined as force, which is mass times acceleration, and the SI unit is a Newton. That's a kilogram meter per second squared. And I'm just giving you this information just to give you context so that you can understand where all of this stuff comes from, because it's all related. okay, and that's a Newton. Okay, pressure is force per unit area. So we've got force and area. Area would be the surface area, length times width. So we have a Newton meter squared, or a Newton distance squared. So the SI unit is a Pascal, which is equal to a Newton meter squared. That is the SI unit of pressure. Now, we don't use Pascals very often because they're really, really tiny. Okay, so we will be talking a little bit more about what units we use in just a little bit and how they relate to this SI unit of pressure, which is a Pascal. Okay. So gas molecules, they collide with surfaces and they create pressure. Okay, so when gas molecules hit surfaces, it creates a pressure on that surface. So when we're talking about pressure and density and all of those kinds of things, we have to understand when we're talking about gases that the more gas is packed into the same space, the more pressure is going to be on those same spaces. So if we talk about the walls of the jar here, the walls of the first jar has lower pressure because there are fewer molecules. But if we pack more atoms and molecules of gas in there, then it has higher pressure. So there are a couple ways that we can change the pressure. We can change the pressure by adding more substance. We can change the pressure by increasing the temperature, because that means the molecules are moving faster. And if they're moving faster, they're exerting more force on the same amount of area. So there are several ways to change that, but we always need to be thinking about the fact that pressure is always this type of what force are you hitting the surface with? What force are you hitting the surface with? And that defines pressure for us. So standard units of pressure. This is where we get into this idea of units. So I'm going to give you a litany. So you will notice that down here is the unit for, yes, down here is the unit for the SI unit, Pascal. See how big that is? 101,325 pascals. That's really, really tiny compared to some of these other units. So one that we use very often is atmospheres. So 101,325 pascals is equal to 1 atmosphere. It's also equal to 760.0 millimeters of mercury, which is also equal to 760.0 torr. Those two things are related. We'll talk about that in a minute. It's also equal to 29.92 inches of mercury, which are similar to millimeters, but of course in inches. It's also equal to 14.7 psi. That's pressure in the square inch or something like that. Okay. And then we have 101.325 kPa. So we actually use kPa more than we use PA, just to let you know. But it's always important to have these down. So it's a really good idea to make sure you write these down in your notes and make sure you highlight them, because this is the key to any kind of problem that you're going to have with gases, especially if you're asked for it in one unit and you're given something in another unit. You need to make sure that you know these things. And the most common ones are going to be atmosphere, millimeters of mercury, torr, kPa. These are imperial units. So when we talk about our barometric pressure is going to be in inches of mercury here in the United States. The pressure that's in our tires is in PSI. So that's why I give you those, but we don't use those in chemistry very often. Okay, so now you can do dimensional analysis. That means you can convert between the units. So how do we do that? At sea level, all of the above define standard pressure. So 1 atmosphere is considered standard pressure. So when we talk about this idea of STP, P is defined as one of these things up here, but usually we say 1 ATM, 1 atmosphere. So we'll get to STP in a little bit of a later date. So the SI unit of pressure is the Pascal, and it's named after Blaise Pascal. He gave it its name because he's the one that kind of came up with this idea in the end. So exercise 1, what can we do here? So the pressure of a gas is measured as 49 torr. I want to know this pressure in both atmospheres and pascals. So I'm just going to do a problem. Okay, so I'm going to start with 49 torr. And I want to know how many atmospheres that is. So I'm going to do my conversion. Torr is going to go on the bottom. Atmospheres are going to go on the top. It's 1 atmosphere and 760 torr. Those are equal to one another. And so I end up getting an answer of 0.064 atmospheres. Not too hard, pretty simple. So how do I change that to pascals? It's the same idea. We have 49 torr, okay? And we're trying to find pascals. So we just need the relationship, the conversion factor, and we know that torr should still go on the bottom. Pascals are going to go on the top. We know that there are 760 torr to 101.325 pascals. So the answer for this is 6,500 pascals in significant figures. So pretty simple. It's just really a simple conversion, simple unit conversion. It's not too difficult. All right, how about this one? I want you to rank the following pressures in decreasing order of magnitude. In other words, I want the largest one first, and I want the smallest one last. So what we need to do is we need to get them in common units. And so this is what I'm going to suggest. I know something about torr in millimeters of mercury. They're very similar. In fact, 760 torr is equal to 760 millimeters of mercury. So that means that these two are already in a unit that I know about. That means that 350 is greater than 300. I know that. So why don't I go ahead and change atmospheres to millimeters of mercury torr? So I'm going to take 0.60 atm. I'm going to change it to torr. And I'm going to do that by saying, okay, 760 torr in 1 atmosphere. And I get that that is 456 torr. So I know that that's greater than 350. So far, that's my greatest one. Now I want to look at KPA. I'm going to do the same thing. I'm going to change it to torr because I don't have to change torr in millimeters of mercury. That's why I'm doing that. So 75 KPA, and I want to go to torr, and I know that there are 760 torr in 101.325 KPA. It's a kilopascal. Okay, so KPA cancels out, and I get 563 torr. So now I know that 75 KPA is greater than 0.060 atm is greater than 350 millimeters of mercury is greater than 300 torr. It's pretty simple. It's just a matter of trying to think it through. Again, I changed to torr only because torr and millimeters of mercury are pretty much the same unit. They have the same equivalence. So I didn't have to convert those two. So I only had 2 conversion problems to do. If I had done it any other way, I'd have to do 3 conversion problems and convert torr and millimeters of mercury into something else. So that was the only reason that I did that. And I came up with the same answer no matter what I do. So I want to know about instruments that measure pressure. So first of all, the first kind of instrument that we're going to talk about here is a barometer. A barometer was invented by Evangelista Torricelli in 1643. Yes, he's Italian. That's why Torricelli. He uses the height of the column of mercury to measure the pressure of the gas, especially atmospheric pressure. This is also known as, a barometer is also known as a closed tubed manometer. And we'll be talking about a manometer a little bit later, okay? But a closed tube manometer. So we get a couple of units from this. Obviously, we've got Torricelli, and we're also measuring a column of mercury. So if you start thinking about that and thinking about the 2 things that were the same, we've got Torricelli, and we've got millimeters of mercury. How far up in metric system millimeters do we have? So millimeters of mercury and torr. 1 millimeter of mercury is equal to 1 torr, and that's where it came from to originate. Okay, so this is what a barometer typically looks like. Now we have different kinds of barometers, but this was the original. He basically had a dish of mercury. He created a vacuum in a tube that sucked up mercury into the dish, and then he relied on atmospheric pressure to determine what was happening. And he could measure he could measure how tall above the liquid of mercury the column got. And that would tell him the pressure of the atmosphere, because the atmospheric pressure was pushing down on the mercury liquid outside the tube. And there was no gas inside the tube, so it was sucking it up, or it was pulling it up. So the pressure would cause that to happen because there was no material inside the tube to prevent it from happening. And so this is where we get this idea of atmospheric pressure. This is basically how we still measure it. In fact, there are lots of ways to do that. So I actually have this kind of barometer at home, and it doesn't give me like, I don't really get number data from it, but I can get this idea, is it low pressure or high pressure? So we need to talk about the pressure of the air and the pressure of the gas that's in the chamber. So when we see we have a gas inside the globe, and then we have pressure outside. So this opening is open and atmospheric pressure is pouring down into this opening. And so we get to understand high or low pressure. So we just have to understand how we do that. So basically, this represents low pressure. And the reason it represents low pressure is because the column of air that's being pushed by the atmosphere is higher in height than the level of the liquid. If it's higher in height, that means that the atmospheric pressure is less than the pressure of gas inside the container, inside the sphere. So we get this idea that the pressure of the gas is the pressure of the air plus the height difference between the two liquids. So we've got this liquid here and this liquid here. So we're talking about the height difference between those two liquids. That's kind of how it works. That's kind of how this kind of barometer works in a lot of ways. So we've got that example of a low pressure example, because the pressure pushing down isn't greater than the pressure of the gas inside the container. Okay, you don't have to have a vacuum for this one. All right, so this one, we see there's something a little different. We see that the level of the water inside the sphere is greater than the level of the water inside the little tube here, okay? And what that's telling us is that this is high pressure. There's more atmospheric pressure pushing down than there is pressure of the gas inside pushing down. So we get this idea that the pressure of the gas is the pressure of the air minus the height. So that would be the difference between the liquid here and the liquid here. What's the difference between that? And then we could calculate that if we really wanted to. I basically use it just to say it's high pressure or low pressure. And I know that because of the way it's looking. I always have to think about it like, okay, what does that mean? If I'm pushing further, it would be down further. If I'm pushing less, then it would be up further. So I always have to think about it, but that's kind of the way I read it. That's a barometer. It's also known as a closed tube manometer. So the second kind of instrument that we use a lot is called a manometer. And we see this a lot in physical chemistry. This was developed by a guy named Otto von Guericke. Actually, it's Guericke. It's German. I don't know. I'm trying real hard. It was invented in 1661, so not too long after Torricelli invented the barometer. But the difference here is that Otto von Guericke actually developed a vacuum pump, and this is what caused him to be able to do this. And a manometer in most cases has two openings. It has an opening to the atmosphere and it has an opening to another gas that you can put in there. And so then we have to look at it from a little bit of a different perspective. So a lot of the manometers that you're going to see here, you're not shown the other end where the gas is put in. But I have used manometers quite often in physical chemistry labs. So this is something that you will see in PChem labs. So the pressure of the gas is given by the height difference in the mercury levels, units of torr or millimeters of mercury. So torr and millimeters of mercury are basically the same. So when we look at a manometer, here we have a manometer that looks like this. So we've got atmospheric pressure pushing down, we've got the gas here, and there's usually some way to put gas in here so that you can figure that out. But we can see the column of the height. So the pressure of the gas is the pressure of the atmosphere minus whatever the height of the column is here. And so you can see the pressure of the atmosphere is pushing down further. So it's higher pressure in the atmosphere than pressure in the gas, which is why we're going to subtract, because the atmosphere is higher, pushing down further. Okay, so pressure of the gas, pressure of the atmosphere minus height. I know that's confusing, but think about it. if the pressure of the atmosphere is pushing further down on it, making the column higher on the other side, the gas inside the container has less pressure than the atmosphere. So you just kind of think through it, okay? Here's another example. This is an example of where the pressure of the atmosphere is much lower. And so instead of subtracting it, we're gonna add it. So the pressure of the atmosphere plus whatever the height difference is going to be the pressure of the gas. And it's because of the difference here. So if this is higher than the liquid level over here, then we have a difference and we're going to add them together to find the pressure of the gas. Okay, so let's look at this. On a certain day, a barometer indicated that the atmospheric pressure is 767.4 torr. A sample of gas is placed in an open-ended mercury manometer. A meter stick is used to measure the height of the mercury above the bottom of the manometer. The level of mercury in the open arm of the manometer has measured height of 136.4 millimeters, and that in the arm that is contacted with the gas has a height of 103.8. What is the pressure of the gas in atmospheres and in kPa? So let's first of all draw what we're seeing. So we've got this tube over here, just like we saw before. It's connected over here to the gas outlet. I know I'm not drawing very, very nicely, but you get the idea. Okay, and we see that the arm that is connected to the outside pressure, that's right there, is here at 136.4 millimeters of mercury. And we can see that the arm over here is right here at 103.8 millimeters of mercury. So we've got filling right here. This is what we got. And there's a gas in here. Okay, so how are we going to figure this out? Well, we know what the pressure is for the day. The pressure for the day is 767.4 torr. The question is, are we going to subtract or add? Are we going to subtract or add? So we can clearly see that the pressure of the gas is greater than the pressure of the atmosphere. And because it's greater, we're going to add. So we need to add the height to that. So the first thing that we're going to do is we're going to take 136.4 minus 103.8, and we get a difference of, hang on, I don't have this memorized. We get a difference of 32.6 millimeters of mercury. So basically what we're going to do is we're going to add, that's H. So we have 767.4 plus 32.6, which is going to give us 800 torr. But we want it in atmospheres, so okay, 800 torr in atmospheres. So we've got to take 760 torr, 1 atmosphere, and we get 1.052 atmospheres. Now, if we want it in kPa, very similar. We have 800 torr. We want to know kPa. So 760 is still going to be on the bottom because that's what it equals to. 101.325 kPa. And we get 106.7 kPa. So it's always a really good idea to draw a picture here. I always have to draw a picture to make sure that I understand if I'm going to add or if I'm going to subtract. And adding means that the gas is greater than the atmospheric pressure. Subtracting means that the gas is less than the atmospheric pressure. So that's kind of how I help myself to remember it. So a little introduction to the kinetic molecular theory. We will deal with this much more later on. This idea that there are some assumptions about this thing that we call the kinetic molecular theory. And some of the assumptions are this. Our particles are in constant random motion. There's nothing predicted about it. It's completely and utterly random, and they're always moving. They never stop. All collisions between particles are perfectly elastic. That means when they hit each other, they completely bounce off. Nothing happens. 3, the volume of the particles of the gas is negligible. So the volume of the particles doesn't really count. We don't even think about it. And 4, the average kinetic energy of the molecule is basically its Kelvin temperature. So these are 4 things that we assume about this model. Now, I am not saying that all of these things are completely and utterly true. We know that according to what we understand about matter, that all matter has volume because it's matter. But we're saying, it's not that big of a deal. And for the most part, those are good assumptions. That's a good assumption. It's also a pretty good assumption that the collisions between particles are perfectly elastic because the vast majority are. There are some that are not, okay? And then, of course, average kinetic energy is related to temperature. We've known that for a while because we know that temperature is the measurement of the average kinetic energy. And we also understand that constant random motion. I mean, these things aren't sentient beings that are talking about, I'm going here. They are just moving based upon where they've hit and where they're going in the next place. So it makes sense. There are some things that are assumed that are not exactly 100% true. And I want you to keep that in mind. All right, so this idea of collisions. An elastic collision is one in which when you hit them, they all fly away, kind of like in billiards. If you think about, playing pool, when your cue ball hits the balls, they don't stick together. They don't stick together because they're hard. It's an elastic collision. It hits and then they bounce off. They transfer energy through that hit. Usually the cue ball is transferring energy to the ball that was stationary. And hopefully if you get it right, it transfers enough energy to get it in the pocket. That's the idea. Now, an inelastic collision is kind of like if you take 2 pieces of clay and you throw them together. If you throw them together with enough force, those pieces of clay will stick together. The same thing happens in a car crash when cars stick together. So if 2 cars are going and they stick together, that's an inelastic collision because now they are together and their motion is a collective motion based upon the motion of the 2. And that is inelastic. We are assuming that all gaseous particles produce completely elastic collisions, and they never collide together and stick. And we know that that's not true, because if that's true, then we would have no chemical reactions in gaseous form. So there are some assumptions made here, but just keep thinking about what we're talking about and where we're going with this. So this theory neglects any intermolecular forces. So it neglects any forces that might be between the molecules. So we're saying none of those forces exist. It's also important to note, I've been saying this, that gases expand to fill their container, but solids and liquids do not. So gases behave differently than solids and liquids do. And we also need to understand that gases are compressible. So if we don't have a container that is expandable, we can actually put a lot of gas in it, or we can take a container that's expandable and push the gas together. And we know that that happens with gases, but it doesn't happen with solids and liquids, which is why we spend a lot of time talking about gases separately because of the behavior of those gases that is so different.